Good morning, good afternoon, good evening, wherever you are. Welcome back to the channel. My name is Opio Oscar. Today we are presenting our machine learning project, that is machine learning approach to database risk prediction and extreme label scarcity based on semi-supervised and positive unlabeled learning. And in this case, our presenters, we have Sandra, we have me Oscar, we have Richard Ugwal, and they'll take over from where I'll leave. So first of all, what are we going to discuss today? Today we shall basically look at the background, introduction, problem statement. We shall look at research questions and objectives. We shall look at research methodology, anti-thorough, comparative analysis, practical recommendations, future work, and acknowledgements. So let's begin with background and introduction. So diabetes mellitus is a chronic metabolic disorder that affects about or over 537 million adults globally, with the projection that by 2045 it will exceed 700 million. So we see that early detection is really very essential to prevent severe complications such as cardiovascular disease, kidney failure, and blindness. So we also see that traditional screening relies on biomedical tests such as HbA1c and fasting blood glucose, which are often inaccessible in low resource environments. And another thing, you see that in rural healthcare system, three label scarcity scenarios always arise. And what are the three? One, we see no labels. In this case, we apply unsupervised learning. Then two, few labels. In this case, we apply semi-supervised learning. And then the third one is only positive labels, where we apply that's positive and label or PU learning. Now, another important thing is, what's our problem statement, or what kind of problem are we trying to solve, or what kind of challenge are we working on? So we normally see that in low resource regions, many individuals with diabetes remain undiagnosed due to limited access to clinical testing, which is true especially in African countries. Then we see that also symptom-based screening could enable early detection, but predictive models must be robust to reality that patient records lack confirmed cases. This is what drive our research. And in our next slide, we are looking at what are our research questions and research objectives. So let us begin with our guiding questions. So the first one is, can supervised learning identify patient subgroups linked to diabetes risk? That's one thing we're interested in to answer. Then two, does semi-supervised learning outperform a supervised baseline when only a fraction of labels are available? That's a second question. Then the third question is, how effective is PU learning in detecting hidden patterns when only positive cases are known? Then fourth and last, which learning paradigm is optimal under different label availability scenarios? Then our research objectives: one, that's to perform experimental data analysis with at least 25 visualizations. So why do we do this? It helps us to understand feature distributions, correlations, and class separability. Then two, we want to implement and evaluate unsupervised clustering algorithms. In this case, we have K-means, GMM, DBSCAN, hierarchical clustering, and assess their alignment with the true labels. Then third, to implement and evaluate semi-supervised learning methods. Then fourth, to implement and evaluate PU learning techniques. Then the fifth objective, to compare all approaches and derive practical recommendations, of which we shall see at the end of the presentation. Now, what's our research methodology? In this case, we follow a structured approach, that is from or beginning with data loading through interpretation. So what do we begin with? In this case, we begin by loading the data from the source. In this case, our source is a .csv file that contains our clinical records or our data. Then secondly, we go ahead to pre-process. This involves removing of null values, detecting duplicates, and we make sure remove them. Then three, we do experimental data analysis. In this case, we use storytelling or visualization to help us understand the nature of data we are dealing with. where we have graphs and pie charts to help us better visualize the data. Then fourth, there's modeling. In this case, we implement models that will help us to make accurate predictions or near accurate predictions. Then we do evaluation of the models to help us come with the best overall model. After doing evaluation of definitely there will be results, then you go ahead to interpret the results. Now let's look at the data set we're having. In this case, we have a total of, that is 520 records characterizing of 17 features, of which we have age, gender, and 15 other symptoms. Then the classes we have, that is 60 positive classes and 40 negative classes. Missing value, fortunately we don't have any missing value. Then split protocol, that's PU aware, stratified. Now let's look at univariate analysis. In this case, we basically look at the distribution of the features or the variables with the diabetes. In this case, we see that our distribution follows a bell-shaped curve, or a normal distribution. Sometimes you find the distribution is left skewed, and sometimes you find the distribution is right skewed. So the nature of distribution helps you to make an informed decision on the next step of action to take. In this case, if it is right skewed, what do you do? If left skewed, what do you do? So if you look at age distribution, it is almost follows a normal distribution. That's for basically for univariate analysis. Now we look at bivariate analysis, where we compare basically two features and their contribution to diabetes. So we basically look at quite a number of features where we're having polygazia versus diabetes. We're having weakness versus diabetes. We have genital thrush versus diabetes, and we can do as many bivariate analysis as you can. Now we also go ahead to do a pair plot of the topmost 5 predictive features, as you can see in the visualization. Now, still by looking at distribution by gender and diabetes, we see that our distribution follows a normal, almost a normal distribution. Now, from here, my other colleague Richard will take over. You're welcome, Richard.
So I will take up from here. That is an unsupervised learning method. Since most of our data is actually unlabeled, we applied clustering techniques to discover the pattern. We actually use k-means clustering, where number of clusters is selected using the Helbo method. Then also we use a Gaussian mixers model, which provides a probabilistic clustering, and also at the same time we use DBScan to help us determine the dense region and identify the outliers. Basically, the hierarchy allows us to visualize the relationship between data points using this matrix. Then we shall also look at semi-supervised learning. This is also one of another method that we use. So we actually use a label propagation, which actually spread levels through a graph based on the similarity between the data points. We also use a label spreading, which improve robustness by using a normalized graph and parameters. I think that one is actually in our other visualization, of which we didn't have that provision to create. Then we are also handling positive and level learning. Now here we were able to use approaches like two-step PU, of which we first train the classifier using a label, positive and unlabeled data. Then we identify a reliable negative from unlabeled data. These are sample with low probability of being positive. And then also basically we have a second approach, that is PU bagging. PU bagging, where we created 20 bootstraps. Sample. Each samples include all positive cases and randomly selected unlabeled data treated as negative. So addition, this is just to help us on each sample. We can get the final prediction using majority voting. This approach can help to improve robustness and reduce noise in our dataset. And then basically now coming to evaluation metrics and baseline. Basically, we evaluate our models using accuracy on unlabeled data and hidden positive detection rate. The detection of hidden positive cases is especially important in the study. However, the accuracy alone can be misleading in the context because identifying hidden diabetes may be treated as a false positive. Therefore, we focus on the better metrics such as precision recall and also recall itself, which better captures the model's ability to detect true positive cases. Then now this is basically unsupervised learning result based on our evaluation, where we can see like DB scan was highly performing in a single score, therefore was actually having the highest score within that one, meaning data points were close to one another. Then also coming to unsupervised learning, still within the same evaluation metrics that we use, the interpretation gives us that supervised learning reveals a clinical meaningful subgroup. This can therefore help us to make a very good clinical decision support based on this data in the interpretation of all this method we are trying to detect with the diabetes in patients. Then also coming to semi-supervised learning, then we realize like 10% of the semi-supervised learning score also higher. That is now on a positive level. Then also supervised learning, we were able to get 73% scores. That's actually based on accuracy in each and every analysis we are trying to give. Basically on this previous slide, we realized like for example, like 10% of level data semi-supervised achieve like 84% compared to 73 for supervised learning. This therefore demonstrates the value of leveraging unleveled data. Now coming to PU learning result, we can therefore see like the PU bagging actually achieve 92% accuracy on unleveled data and recover 94% of hidden positive cases. This makes it highly effective for detecting undiagnosed and unknown diabetes rather in patients. Then now coming now to comparative analysis, we can see now the model performance. Actually now the metrics that we use, like in PU learning, basing on the level positive data wholly, we were having the score of 0.9, and also semi-supervised, that is now both level and unlevel, we were having accuracy of 0.89, of which is fairly in the prediction, fairly good rather. Then also supervised learning using K-mean, we were having literally only 0.42 ARI, that is only on no level data. So therefore in this performance, PU learning was able to give us a very clear prediction in all this method that we use. So now coming to limitation and a clinical study within this clinical study, we realized like our data scope and validity The study relies on a single source of datasets of moderate size, 5.2, of which um, it was not enough to really cut us uh, all the problem which is affecting the entire prediction within database. Meaning, if we are having a very many data set, we would really extend our analysis further. Then we compare the outputs in each and every data set. That would really make us to give a clear conclusion. And then simple encoding limitation. We realize like symptoms are encoded as binary, of which is symptom alone. This symptom alone, which were recorded as yes or no, were not enough to really confirm to us whether our detection were really true in our analysis. So we really needed like some other simple like symptom duration, intensity, and frequency. So these were not captured in the dataset. This was also one of the limitations in this study. Then a cynical deployment. Also, we this deployment is just actually to enhance clinical decision support, but should not be done without the medical oversight. Then a practical recommendation, we would actually recommend the use of only positive level data to really give us a clear prediction. Also semi-supervised learning, basing on the result that we were able to realize, we would not really encourage, but the use of positive one we would really encourage, since it will not be misleading. So our future work that we are projecting, like expanding dataset to cover multiple clinic site, then also like fairness and biasness. We don't want to actually cover only gender and ages. We really need to capture some other attributes in this analysis, so that we can really come up with a clear prediction with a high degree of accuracy. Then these are references for our studies. Our acknowledgement goes to our team for all the work that we are able to present, and also moving further with it. And also at the same time, we give back that gratitude to our instructors who are helping us through all these research studies, so that we can make a better decision that can be informed to the necessary stakeholders.